Good morning, good afternoon, good evening to everybody. Welcome to the special Delta Lake High Performance webinar. My name is Denny Lee, and I'm here with Jay and Chen Chen. I'm going to have them introduce yourselves, but we're doing a special live session at the Eventual HQ. On Beyond JVMs, reinventing catalogs with Delta Lake and Daft. So without further ado, I want to let Jay and Chen Chen introduce themselves, and we're going to dive right into it. If you have any questions, definitely chime in on whether you're on YouTube or LinkedIn or on the Restream platform, and we'll get to them as fast as we can. So without further ado, I'm going to hand this mic off to Jay, and we're going to go from there.
Thank you, Denny. Hi, everyone. My name is Jay. I'm one of the co-founders at Eventual, and we are behind the Daft open source query engine. I'm joined here by Chan Chan. Maybe a quick introduction. Yeah, my background is I used to work in self-driving, and then before that, biotech. So I've been working in a lot of weird data modalities, right? Like you might think to yourself, oh, can I store like videos and images in Delta Lake? That's the sort of stuff that we used to work with in self-driving. And so we'll be going through some of that today, which I'm pretty excited about. And I'm joined here by Chan Chan.
Hi everyone, I'm Chan Chan. I lead community at Daft, and I just started my DevRel journey about 2 years ago, so really excited about what's going on in the open source world and just trying to grow our community around Daft.
Cool. I guess maybe let's jump right into it, into the content we have prepared for today. So maybe a quick introduction about what we're doing with Daft. Daft provides simple, reliable, and performant data processing of any data at any scale. This is how you install Daft. It's a pip installable Python library. You just do pip install Daft and you're kind of ready to go. Everything is all packaged into this one really nice Python package for you. Under the hood, it's all written in Rust, but to the user, to you, it looks like it's all just in Python. So, already done quick intros. Yes, I'm originally from Singapore. Now we're out in sunny San Francisco, where we all currently are right now. And yes, I'm a data person, data warehousing, machine learning, AI, data infrastructure. And then, things I've built include distributed training, data loading, right? Imagine you have a large warehouse of data. How do you feed that into your models for training? And also kind of data warehousing in the health, bio, or autonomous vehicle space. And now kind of behind the Daft distributed data engine. Maybe Chan Chan quickly as well.
Yeah. Just to quickly introduce myself, I'm Chan Chan again. I live in San Francisco. I'm actually born and raised in the Bay Area. I started my DevRel journey at a startup called Alexio, where I was kind of introduced to the open source ecosystem and like learning what it really means to be a community evangelist and a community manager. And then I joined Daft in August of last year, just really growing the community around Daft, whether it's hosting meetups around the Bay Area or getting involved with open source projects like Delta Lake and just, everything Daft related. Yeah.
All right, let's dive into it. So today's agenda. First, we'll go through kind of a brief history of open table formats. I put it in quotes because I think they're much more open now. We can go through that in a little bit. And then also do a little bit of a demo with Daft and Delta Lake. So, all right, let's dive into the brief history. I did a Google search, big data technologies, right? And this is kind of what came up. We see Hadoop, we see Flink, Spark, of course, Samza, MapReduce, man.
Oh, that's going for
And I know, but what's the one common thing across all these things that popped up when I searched it? They're all built in the JVM. And I think this is pretty understandable, right? Because back in the day, Java was kind of the language for the enterprise. Everything could run on Java. You would, install Java on a cluster of machines and almost have this guarantee that any software you want to run runs on that JVM. And if you wanted to make things faster, you just kind of improved your JVM and everything else automatically got better. And so there was this whole ecosystem built around Java, where big data really emerged. And, but here's the pitch, why care about Python, right? I think Reynold over at Databricks, I've dug this quote up from somewhere, I forget where, but he said, probably 80% of Spark users use Python, right? And I think it's really because of this really special relationship between the three, what I consider to be the main pillars of data. You have analytics, you have data engineering, and then you have machine learning and AI. And I think SQL and SQL that runs on the JVM sits in this really nice intersection between analytics and a little bit of data engineering, right? If you want to do any analytical query, it's very expressible. In SQL, you do group by, aggregation, join, and window functions. And that's very nice to use from SQL, and also surprisingly quite nice in data engineering as well. If you want to be able to do transformations, read and write from like certain data sources, if everything is nice and expressible from SQL, then it works pretty well. However, this world of like machine learning and AI has almost been this like orphan child of the ecosystem. I don't know if you would agree, but oftentimes what I see is that people will export all the data and then now use Python in like a machine somewhere to process that data. And that's because I think Python sits at this really interesting intersection of it can do analytics with PySpark, it can do data engineering, and in fact, people often use it for data engineering because there's all this like messy data that you might want to just run some Python on. And the last thing is that it's almost a must for ML and AI because the entire ecosystem is kind of built around it. And so, yeah, that's why I think the ecosystem should care about Python. And I think we're moving to a world where data is now basically SQL and Python, both of them. And so I guess like why has this world been hard to build historically, right? So diving a little bit into it, Delta Lake itself is really just a protocol. It's like a specification, right? You can read about the specification online, but the actual implementation of it, and I took a screenshot of the Delta Lake 3.3.0, I think was very recent.
Like a few months ago.
Yeah, just like a few months ago. And if you look into the GitHub, the officially vendor implementation is for a JVM-based system, right? It releases a jar, which is meant to be installed from the JVM. Similarly, another kind of cornerstone of the data world today, Parquet, which is a on-disk file format, is also a protocol. If you go to the official Parquet GitHub, it's all in this one thrift file, which is just a definition of like all the stuff in the Parquet file, right? It's a protocol. There's no implementation detail. And also similarly, the vendor implementation of the Parquet protocol is actually also meant for the JVM.
Yes.
And so back in the day, unfortunately, in order to use any of this stuff, to use Delta Lake or Parquet, you need to install the Delta jar, the Parquet jar, and that means that really only systems like Spark could use this stuff, systems that were built in the JVM. But I think what's exciting is that, in today's world, there's a ton of really new interesting projects coming out. I put together the two main ones that make today's demos possible. So the first one is this idea of like, Delta Lake is going rusty.
Absolutely.
Yeah.
Yes.
Where we have Rust as a common implementation layer of the Delta Lake protocol, and then other kind of packages built on top of it. So Python and Rust actually is a great, it's very easy to interoperate between Python and Rust, which is actually what we use in Daft internally as well. But in the Delta Lake, Delta RS, and also the Delta Lake Python package, that's what they use. And so now there's a Python interface to Delta Lake, which is really amazing. I think the second thing that has really happened over the last few years is the introduction of Apache Arrow. If you're not familiar with Apache Arrow, it's an in-memory format specifically built for interoperability between languages, right? And so I think because of that goal, they've kind of successfully made a lot of these on-disk formats interestingly accessible, because now the Parquet C++ library actually now belongs to the Arrow C++ project, which means that from any language you can now kind of go through this one common narrow ways, which is Arrow, and then access formats like Parquet. And so that makes projects like Daft, Pandas, DuckDB, Polars, all of these different query engines, which are primarily meant to be used from Python. Now we can really talk the Delta Lake protocol and talk the Parquet protocol and interact with all these systems, which is extremely exciting because now I think we're truly in this new world of like open table formats. Because yes, although the specifications in the past were open, now even the implementations are open and fairly mature, meaning that we can now really talk this same language. So I think that was kind of a quick overview on like the things that we're covering today. Maybe just quickly, what is Daft itself? So Daft is a data engine for across those three intersections that I talked about: data engineering, analytics, ML, and AI. This is how you install it: pip install Daft. We support both a SQL and DataFrame interface, which we can show off in a bit. But in order to use Daft, you just kind of import it from a Python session. It's like import Daft. Here's creating a Daft data frame from a Python dictionary. Very simple. We support all of the kind of analytical, kind of cornerstones of what we do with our data frames and our tables. So this is an example of running a mean, right? And Daft is also lazy, meaning that if you run a mean, it doesn't run that operation right away. You have to tell Daft, please show me like a couple of rows, and that executes the Daft engine. This is how you run SQL. So Daft also supports SQL. You can do daft.sql and pass in SQL strings, and it works pretty well out of the box as well. And yeah, so one interesting thing is that Daft is really, really good at local execution, right? So when we built it, we wanted it to work kind of just out of the box locally on a single machine. I have this long rant on Twitter about like software today needs to be able to be like apt installable and go. Like you shouldn't need to install like Docker or like Zookeeper or like anything like that to get your software to work, right? And so we built Daft with this really strong, I guess, philosophy of when you're on your local laptop on a single machine. If you're on like a MacBook Pro, you have like an M4 chip. It's so fast and it should really work super well. And so when you run Daft by default, it runs on this like super streamlined streaming execution engine that runs on a local view. So, and we run actually on a, I guess, sister project of Spark called Ray. And so if you have an existing Ray cluster, just gonna point Daft at it, just like this, and it will just automatically run on that Ray cluster, giving you that ability to just scale up in the cloud when you need to. And yeah, that was a little bit about Daft and kind of how it all works. I'm going to pass the time off to Chan Chan now, who's going to show us a quick demo on Daft plus Delta Lake. What does that interoperability look like, and why this is also exciting for I guess, the data world at large.
Yeah. Okay, cool. So Jay just gave a great overview of Daft and a little bit history. Now let's actually see Daft in action. So we're going to use Daft to explore the COCO dataset. COCO stands for Common Objects in Context. It's a large-scale object detection, segmentation, and captioning dataset for images. So for example, in this image with snowboarders, we see that the dataset has segmented the different snowboarders in the image as well as the snowboards in the image. So let's see what Daft can do. Like Jay said earlier, we can just install Daft with pip install Daft and it'll just work out of the box. But actually, with our native integration with Delta Lake, we can install all the Delta Lake Python packages to fetch metadata about the Delta Lake table, such as the paths to underlying Parquet files and data statistics. So again, we're not dealing with any jars or JVMs that need to be installed. This is all purely Python and Rust code, and it just works. Great, it just worked. Daft can read from several data sources like in memory from a pandas data frame or a pyro table. Daft can read from several files like Parquet, CSV, JSON, and also catalogs like Delta Lake, but also Iceberg and Hudi. So for this demo, let's read the Parquet files from the COCO dataset. Okay, and no data to display. What does that mean? So again, Daft is lazy, which means that the contents from the data frame will not be materialized until we explicitly tell Daft to do so. So we can call a .show to materialize the data frame. Great. So here's a little snapshot of our COCO dataset. So Daft has built-in expressions to do common operations with multimodal data. For example, people often store images outside of their tables. So in our data frame, we have this bucket URL column of images in S3. So with Daft, we can download these images and then decode them. Oh, oops. So we have our beautiful images from the COCO dataset on the right side. So you can actually do this with other data frame libraries by writing UDFs or user-defined functions for URL downloads and image decodes. However, the magic of Daft is that this is all natively implemented, and also written in Rust for performance. So if you were to monitor your machine's resource usage, Daft actually maximizes both network I/O and CPU usage through streaming. So just a little bit of background. When we're designing an execution engine, there are two main considerations for synchronizing data flow. One is bulk synchronous, and the other is streaming. So in a bulk synchronous model, operators work in distinct sequential stages where each operator has to fully complete its task or its execution before it gets passed on to the next operator. So with this model, it'll use a lot of memory and a lot of resources because first we have to read the whole data set, then we download all of the URLs, then we decode all of the images. It's a very inefficient process. So Daft's execution engine uses a streaming model where data flows continuously between operators in smaller incremental chunks. So each operator will process a little bit of data, send it to the next step, download the URL, send it to the next step, and then decode the images. So with this streaming model, the Parquet reads, the URL downloads, and the image decodes are all pipelined together and executed in parallel. So you can see Daft here is maximizing resource utilization across all these different steps by utilizing both CPU and network at the same time. Okay, cool. So we kind of just ran through what Daft can do. Now let's take a look at how Daft and Delta Lake can work together. So we already have our data frame of images. Now let's also pull the categories and the annotations from the Cocoa dataset, and then we will join all three of them together. Okay, so here we have the categories, then we have the annotations, and then we will join all three. Great. So from category ID to bucket URL, this was our original images data frame. From area to segmentation, this is our annotations. And then from super category and name, those are from the categories. Cool. So what can we do with this? Daft has native support for reads and writes of Delta Lake tables. So now we can write our join data frame to Delta Lake partitioned by categories. Great. Okay, so we successfully ran to Delta Lake, and then we can see here in our file directory that we have a images table. I just need to delete this for later, sorry. And inside our table, we see our partitions, we see the Delta log. So we saw that it worked. Let's just, for fun, read it back to make sure that it worked. We have this red warning, and it says Delta Lake scan operator has partitioning keys, but no partition filter was specified. This makes sense because we did a df.collect, and what that does it will read the entire table and read all of the data. But instead, to actually take full advantage of the Delta Lake table format, let's only read the partition that we care about. So, for example, I only want to see the animals from this data set. So instead of reading all of the data, we can filter for animals. So let's reread our table. Let's add a filter, and then let's select a couple columns. Okay, and then just to explain, so what's happening under the hood right now? What is going on? So we can actually use .explain to look at the logical and physical plans for the filter and select operations. Okay, so a great bonus of Daft is that Daft supports data skipping, which means that instead of reading your entire table, we're only going to read the partition that we actually care about. And we can actually visualize this in our logical to physical plans. So first, we have our unoptimized logical plan. This is your literal order of operations that we gave our engine. So this is reading the table. This is filtering, and then we will select our columns. So Daft will take this unoptimized plan and then optimize it for more efficient computations, for better use of resources. So we have our optimized plan here. So we're reading the table, but instead in here, we can see that we have a partition filter on the category animal. So instead of reading the whole table, we are just reading on the partition, and then we will select our columns. And then once we translate the logical plan to the physical plan, we can also visualize the data skipping here. So we have the scan task source, which is just reading the data, but then the actual scan task, there shouldn't be two, but the actual scan task shows that we are reading the category animal. And then we're selecting our columns. Great. So that was a kind of overview of Daft and Delta Lake. And we mentioned multimodal earlier. What does that look like? So as shown earlier, Daft can decode images from the S3 URLs. Cool. So this is the data frame that we had earlier. And we are only showing animals. So in these images, we see dogs. I guess in this one, like I can't really tell where the animal is. So we can actually crop these images based on the bounding box that was provided by the annotations dataset. Cool. So now we have a clear view of like where the animal is. So I guess in this one, it was like in this little corner over here. And then yeah, but like these are all in kind of funky sizes. They're all very different. So well, we can take it one step further, and now we can crop these images, resize them, and then create thumbnails. So let's do that. Great. So now we have all of the images cropped to the same size. And then lastly, what we can do is now encode these images, write them to a Delta Lake table, and then we have a multimodal Delta Lake table. So here we have the images encoded to their binary, and then we will write this table back. Cool. Okay, and then again, if we go to the file directory, we can see here the thumbnail table. So we've successfully written it. But again, just for fun, let's read it back. And then we'll decode the images again to make sure like that is what we want to see. It just takes a little bit of time. Oh, perfect. So if we go all the way to here, we can see these were the thumbnails. These are the images that we expected to see when we wrote our data frame to Delta Lake. Great. So we demoed Daft, we demoed Delta Lake, we demoed multimodal. Can we do even more? Let's throw in some AI because why not? Let's write an AI UDF and make an API call to OpenAI. We're giving it a prompt to rate the fluffiness of the dogs, assess its confidence, and then also provide a reason for its confidence assessment. And again, like this is all purely Python. It's all been working very seamlessly. And then so we're also using a couple libraries to help us make this call and structure our response with instructor and Pydantic. So let's make our OpenAI call. Cool. And then now we have OpenAI's assessments. Let's add the responses to our data frame. And then let's also extract the response and collect. Cool. So if we go to the right here, we have the fluffiness score, we have the confidence, and we have the reason. Let's just zoom into this a little bit and only look at responses that have a fairly high confidence level. Okay, so cool. So we can see here, OpenAI is like fairly confident that this dog is fairly fluffy. And for the reason, it says the dog's fur appears soft and somewhat fluffy, but the image quality is limited, making it difficult to assess the full texture. Another example is that OpenAI is fairly confident that this dog is not that fluffy. And the reasoning is that the dog's fur appears somewhat wiry and not overly fluffy, but there is some texture available. So that's the end of our demo. So we showed off Daft and Delta Lake for a multimodal data and AI workload. And always like to call out again that this was written purely in Python. We did not have to deal with any complexities of the Java-based environments, no jars or anything. And it just all worked with a pip install.
Cool. I forgot. Do we have any other slides left, or we're good? Here?
That's it. I think we have one final slide which we can jump to.
Yeah, why don't we just show that real quick? So,
yeah.
There we go.
You want
Yes.
to take this one with the?
So yeah, thank you. That was the bulk of our presentation. Feel free to join our Slack channel. We're always on there. We're always responding to people. So yeah, please join our community.
Cool. So we got some really good questions popping up. And so for starters, I think the first thing we want to ask is like, thanks for sharing. Could you please point me to the document for Daft? Is it open source? Is this a Databricks product? So I can honestly say, unequivocally say, no, it's not a Databricks product. Okay? So there's no, we are friends, absolutely, but no, this is Daft is created by the team at Eventual. Why don't you guys go ahead and explain a little bit more about Daft, how it's open source, the context behind it, the whole kit and caboodle, please.
Yeah, go for it.
Okay, well, yes, Daft is completely open source. But actually, I feel like Jay has a better explanation of like why we're building Daft, like talking
Yeah.
about the unified.
Yeah. So I think let's first talk about why Daft is open source. I think.
Sure,
Right.
we'll start with that. Yeah.
When we looked at the landscape of like data tools, we saw that there was actually a lot available for SQL and tabular analytical data, right? And I think the interesting thing is that SQL today is almost so well defined that it's fine to just build a closed source thing and have people fire off SQL into the void and have it do something, right? But I think what we realized was that working in the Python ecosystem, which is almost completely an open source ecosystem, if you think about the tools that we use, PySpark, PyTorch, NumPy, scikit-learn, all of those are open source. And in order for us to build a tool that's truly for the community, that allows for developers to use it without needing to sign up or pay for something, that's why we made Daft open source. We believe that like open source tools are really the way to build data tools today. And that's kind of also the philosophy of like, hey, when you use Daft, it should work really, really well on a single machine. But sure, when you do want to scale it up and like have it run on like 100 terabytes of data, like yes, we will be providing some sort of commercial offering to make that easier. But by and large, for most developers, we're running at a scale like iterating on these projects that I don't think it should be gated behind some sort of a commercial product. And then in terms of the motivations behind why we're building Daft in the first place, I think part of it was actually part of this talk where we were very, very frustrated that in order to do anything with data, we had to like at first install Java version 11, and I'm like, I'm a Python developer, and so I think it was born a lot of those frustrations, and also the frustration of hey, why do all these really good tools exist for structured data, for tabular SQL data, but nothing really out there is like built for this idea of like messy unstructured stuff that I run Python on, right? And I think really the ultimate goal of all of this is how do we bring back almost this simplicity that was so key to, if you think back as programmers, the Unix philosophy, right? Everything is just a file. You have standard in, you have standard out. If things go wrong, you have standard error. But yeah, there was no real complexity around this. There's no need to think about like partitioning. There was no need to think about memory. It just kind of all worked. And I think that's really what we're going for here with Daft as a project. Simple, reliable, runs on any data at any scale.
So I'm just curious, actually. It's sort of implied with some of the questions here, but I figured I'd just ask straight up. Like, so how much from the back end is it basically like how much of your code is basically Rust based versus how much of your code is basically Python based in terms of how you built that? I'm just curious from that perspective.
Yeah, so we view Python as a really good interface between us and the user. And so it's almost immediate when you go from a Daft DataFrame call to when it translates it down to Rust. And so all of our planning is done in Rust, which means that if you as a user say, hey, please read some Parquet, run some image, like URL downloads and image decodes, and then write that out to a Parquet file, internally that encodes it as a Rust plan. And then we just execute that purely in Rust. There is a caveat here as if you do a distributed backend to Ray, we do translate our Rust code back into Python to schedule that over the Ray cluster. But by and large, if you are just using Daft SQL, Daft DataFrame on a single machine, all Rust once you get past the initial interface, the Pythonic interface.
Gotcha. So then could users then potentially like just install the Rust crate version and actually try to run it directly? I'm just curious. Don't get me wrong. By the way, I want to call out. This is purely as a Rustation that's asking the question. So in other words, I actually don't think this is a good idea as a general rule, by the way, but just purely as a Rustation, I have to ask that question.
Yeah, you could.
Yeah.
You might find that some of the documentation isn't as solid, I would say.
We have the same problem with Delta Rust. By the
Yes.
way. Yeah. So Delta Rust, like, and so I can ask that question just because we're guilty of this ourselves, right? If you look at what is the most popular way of working with Delta Rust, it's unequivocally the Python APIs, right? That's what people are typically interfacing with. It's just that by the same token, we are like, there's a bunch of us who are like, no, let's just go write the whole thing in Rust and query it using the crates and all that other stuff. And some people love that idea. Most people are going, no, I'd rather not do that. We're like, no, we understand. It's okay. We're not judging you.
Yeah. I think actually on that point though, Rust is a really good builder's language.
Exactly.
So for example, really popular projects like Data Fusion, that's why they're popular.
Absolutely.
Right? Because they are like by the builders for the builders almost.
Yeah.
Whereas I think Daft really is a project that's more for like by the builders and then for the practitioners.
Right.
right,
who are more in the Python land. But yeah, if people are interested in, if any builders are interested in building off of Daft, we would love to chat and see if there might be potentially some avenues for working together there.
Yeah, absolutely. And this is, by the way, why it's so important for us to talk about things in the nature of like Arrow and Data Fusion, just because we're all very reliant on that ecosystem. Just to provide a little context, when we first started creating Delta Rust all those years ago, we actually were helping with PyArrow to Rust Arrow, that type of translation. So that way we could get where we are right now. So it's very much community driven. So I love working with these guys a lot, even though I believe Chan Chan's currently wearing her anti-Spark Social Club t-shirt.
Oh boy, I am too. Show that off, Chan Chan.
Exactly.
Oh no.
Right, exactly. Which is completely cool. Like I said, like even though I'm an author of a Learning Spark book, by the way, yes, I actually completely understand where the context is coming from. You actually hear from a bunch of us from Databricks. In fact, like if we had built Spark now, we probably would have built the thing in Rust, right?
Yes.
So just as a quick call out, just for fun on that.
Yeah, no. I actually think that like Spark is such a solid piece of software. Like, I don't think you can find a single company out there today that's like serious about data that doesn't have Spark somewhere in its stack, right? But I think also that like Spark was built in a world where things were JVM based. It was completely okay to run these things that always run it on a cluster. But I think part of the success of Spark has also been why people are like frustrated with it sometimes.
Oh,
right?
absolutely.
So
Yes, yeah.
yeah, that's kind of where all this comes from.
Yeah. Hopefully you guys can hear me through this mic. Apparently this mic's not as strong, but hopefully you guys can hear properly. I'll just put it a little bit closer to myself. And related to this is like, they have a question here is like, is it possible to use this with DLT or Databricks jobs? DLT most likely not, though I'm sure in the future will be. In the case of Databricks jobs, yeah, I mean, basically one of the most common ways to run a job within Databricks actually is to go ahead and run just a standard Python job, right? And then there you go. And then, by the way, Ray is actually very, very popular within Databricks as well. So exactly as the call out, you want to run a distributed Daft workload, perfect. Daft workload on top of Ray. That is underneath the covers. A very common way to have distributed Ray is actually to have Ray working on top of Spark, whether it's on Databricks or anything else. And so, yeah, there's multiple ways of approaching this particular problem, but that actually is a common workload. And again, part of the reason why I'm here. So, yeah.
We also are teaming up with the Unity Catalog team, and so that's a big focus of ours, because I know that like within Databricks, at least, everything is very Unity Catalog, Delta Lake focus. And so actually Daft works pretty well today. We have people who use Databricks and use Daft on the side to just query Unity Catalog, whether that's single node or distributed, doesn't really matter. I think what's really cool is that Databricks is almost committed to like building this open ecosystem for the data, and now engines like Daft can just come in from anywhere, really, like EC2 machine, laptop, like inside of Databricks, to just read this data and help process it.
Absolutely. So, okay, let's jump into another question. Let's see. Does Daft currently support newer features of Delta Lake, for example, like deletion vectors? And, yeah.
Great question. We do have a roadmap somewhere in our GitHub issues. Deletion vectors, unfortunately, we support that for Iceberg, but not yet Delta Lake. So if folks are interested in that, please thumbs up on that issue, so we know that you're looking at it, and then we can get to that.
But I did want to chime in. Part of the reason's actually not with Daft. Part of the reason's with us, actually, with Delta Rust. So Delta Rust, we've been actually for the last year or so been focusing on what, if you'll look at it, the Delta Kernel RS project. The reason this particular project's interesting is because engines like Daft, among many other engines, are all very interested in using Delta Lake. Cool, we're all happy about that. But then the integration, like for example, getting that work where all of a sudden Daft has to inherently understand all of the metadata, right? We actually are trying to simplify that process. So the project Delta Kernel RS is basically there to abstract away the understanding of the metadata associated. So irrelevant of whether you're looking, like, for example, Delta Lake metadata or Iceberg metadata even. We're all going to be at Iceberg Summit tomorrow, for example. So that's why it's pretty funny that we're at a Delta Lake session talking about Iceberg, right? But the whole context is because we're actually trying to simplify that flow, whether it's from a Delta Lake perspective or even from an Iceberg perspective, where engines don't actually necessarily have to understand inherently what that metadata is. They just have to understand, here's the files I'm supposed to look at, here's the deletion vector I'm supposed to look at, and I'm just going to go float with it. And so, for example, even though Daft already works with Iceberg deletion vectors, which is great, right? Iceberg deletion vectors are made with roaring bitmaps and the Puffin file. Well, guess what? They're also completely compatible with the Delta Lake deletion vectors as well. And so, as soon as we get Delta kernel RS up and running, and we're actually, I think it's like either the 1.0 or like the 0.28 version. I'm trying to remember which part of the roadmap it is, but that's actually within the next couple of months. In fact, we're going to actually have the deletion vectors inside Delta kernel RS, and by having it there, that actually makes things a lot simpler for Daft, for example, to plug into. So there is a version of it that actually works right now that was actually introduced, I want to say 0.19 or 0.20, but again, that was a earlier version and it required inherent understanding of the way Delta implemented it. And so that's why we're talking about the Delta kernel RS, because that way engines like Daft don't actually need to understand this stuff anymore, or at least a lot less painful for them. So yeah. So I'm going to call that on me as opposed to on them for this one. Okay. So just a quick call that.
Yeah, no, that makes sense. I think we are playing a little bit of catch up to the JVM ecosystem, but things are moving very rapidly, which I'm excited about as well.
Yeah. No, from where we're coming from, basically, as you can tell, that like we feel that the Rust ecosystem is sort of the next generation.
Yep.
This doesn't mean that we're not going to be working with a JVM or working with Spark, right?
Yeah.
But by the same token, from where we're sitting from, a lot of value, a lot faster performance, a lot more reliability, less likely to actually fragment and corrupt your memory, is mainly because we can utilize the Rust ecosystem. So that's why we're also very big fans of that ecosystem, and that's why we're here today too. So yeah, cool. Let's see, any other questions? Oh, okay, here we go. Actually, I'll have you answer that, but I sort of started that. Do you see data engineering move toward Rust, Delta Daft? Is Rust highly performant compared to JVM languages? Why do you start, since I've already been chiming in on that?
Yes. So I think one common misconception is that the JVM is slow. I think that's actually a common misconception, because if you look at some of the most highly performant applications in the world today, some of them are built in, say, high performance, high frequency trading. And these firms are big users of the JVM. I think what's interesting is that the JVM itself is extremely performant once it gets like warmed up and has the ability to make predictions about where your code is going. And that's where it gets really, really powerful. I think the problem with the JVM though is that unlocking this performance is very difficult. You have to know what you're doing, basically. A lot of these, just anecdotally, a lot of these high frequency trading firms, they will just like turn off the JVM once a day to get all the garbage collection. Like they turn off garbage collection and they just like turn it off and on like once a day, when the markets are out, right? And so those are things that, the JVM itself is very, very performant, but you have to know how to use it. I think the interesting thing about things like Rust is that it makes it a lot easier and simpler to leverage some of the high performance techniques like SIMD, vectorization, efficient memory, and just a very tight control around memory and not needing to deal with the garbage collector. Do I think that all of data will move towards Rust? I mean, I hope so, but I think realistically, these technologies are embedded within companies today, and we will continue to run technologies on the JVM for a long time. But I do think that like for a lot of more modern workloads, we will see this gradual shift towards things that are definitely more Pythonic. And then once you have Python in the mix, then everything under the hood is kind of just abstracted away, whether that's C++, which, by the way, everyone has been using for a long time too.
Exactly,
like
yeah.
NumPy is like C++, right?
Exactly.
It's all like Python, C++.
And don't forget, just as a little trivia offshoot, half the math algorithms that we're still using are still from Fortran.
Yeah.
Like old school Fortran.
Exactly.
So, yeah, the crap I used to write, actually. Okay, so just as a call out, I'm old. So yeah. So this stuff's still around. Okay, so I'm with you 100% on this one, dude.
Yeah. But I do think that Rust is pretty interesting. We chose Rust because we thought that it would kind of lower the barrier to entry for people who wanted to contribute to high performance, languages. It can be very intimidating to come to a new code base and go like, what are all these C++ like macros, like different, different standards across different code bases. But Rust is very opinionated, and so it makes it very easy for someone to come in. And I think Rust is extremely, extremely compatible with Python. There's a Rust to Python library called Pyo3 that's extremely good. One example is actually if you pass a NumPy array into Rust, it appears natively in Rust as like a view of like the integers, which is amazing, right?
Yeah, exactly. Yeah.
In C++, it's like, I don't know if you've ever worked with PyBind, but oh my goodness,
God, yeah.
nightmares,
Yeah,
right?
yeah.
And I think that really
I'm
just
old
has,
school, right? I used to deal with this.
yeah. So that just it enables the developer who wants to build for the Python ecosystem, but then wants to build high performance tooling. I think that's the real power. So it's not really about whether or not we're all going to move to Rust. I think it's more this general theme of data moving to a world where we have SQL and Python, and then what's
Right.
really powerful for Python today is that Rust ecosystem.
Right. So just to add a little small story, QP Howe was and Tyler Croy were the ones who helped create. Actually, not help create, created Delta Rust.
Mhm.
Okay. What was interesting about it is they first looked at the protocol, just like you're talking about, and they went ahead and said, "Hey, like they caught a bunch of mistakes in the protocol, so we fixed it together." And then they started building Delta Rust right afterwards because they were like, "Hey, you made an assumption," and we're like, "You're right. That is an assumption we shouldn't have made."
Yes.
So they went ahead and wrote Delta Rust. Now, what was interesting about whenever I talked to QP or Tyler, and you can find some old interviews that I did with them on this one too, is that when they originally did it, it wasn't because specifically they were thinking high performance, by the way. They were actually literally going like, do we go with Golang to build our apps, or do we do Rust with apps? I want to geek out on Rust because, to your point exactly, Rust is very opinionated and actually does an amazing job with memory management. So they're going, okay, cool, let's just go do that. And then that I don't have to write the reams of code in C++ like I used to, right? So that's set. And this is all before large language models where they can generate the code. And by the way, anybody that wants to go do that, good luck with it, because now you'll be spending just as much time debugging the code as you are actually writing the code. So I don't know. Good luck with that. But the context was that then they ran it, and I still remember the first time we were testing it and playing it together, and we're like, that can't be right. And we were like, what do you mean? It's like, it finished already. It's like we were going, no, it can't be finished already. That's way too fast. And so we just kept on reviewing over and over again. Like, no, we screwed up something. We must have forgotten something. And then we kept on testing, and then finally we just started testing between the original Delta Spark spec. And then we're going, no, answer's exactly the same. Oh my God, this is so much faster. Then we realized just because of the more efficient memory management, it just finished faster. As simple as that. It just literally finished faster. So we weren't even trying to go fast initially. It was just literally more like, this would be fun and cool to do. And then of course, as soon as we saw how fast it was, we're like, okay, we're going full time on this one. So exactly to Jay's point. I mean, I think if you're already hardcore in the JVM, you're probably not going to leave immediately. But do I see even enterprises that are starting to go toward Rust, even with hard set in the JVM? Actually, yes, I do, and I think that's normal, and I think that's good for the data engineering community as an overall. Anyway, cool. So let's see. Oh, there's a good question here. How does Ray fit in the ecosystem with Spark and Daft? Actually, why don't you talk a little bit more about Ray on the Daft side, and I'll do a small little bit on Spark afterwards.
Yes, makes sense. So Ray is an interesting project. I think like maybe just like Spark in the older days where it was all RDDs and then kind of stuff built on top of RDDs, we should also be thinking about Ray in that sense and not kind of just like, oh, this amorphous blob that is Ray, right? So Ray has Ray core, which is its core set of primitives, including the actors, the Ray remote functions, the Ray tasks. So that's actually what Daft uses to run on top of Ray, right? That core set of primitives. Ray, when people talk about Ray, it also may refer to parts of the ecosystem. So other libraries that are built on top of Ray, maintained by the Ray team, which include, I think most pertinent to this discussion, Ray Data, and then also tools like Ray Train for training models, Ray Serve for serving models. They have like, I think RL-lib, which is a RL reinforcement learning. Exactly, yeah. And so I think Ray as a engine, and the Ray core engine is meant to be this general distributed platform where people can build distributed applications on top of it, just like Daft. And then they have Ray Data, which is their main data abstraction, but it's really also meant for more like last mile processing into your training. And so it's not meant to be a general ETL solution like Spark. And that's, I think, the Ray team has been very consistent. Feel free to call me out on this, by the way, Ray team, if I misrepresent you guys. But yeah, so I think that's kind of how Ray coexists with Spark, right? It's like, hey, if you need to do any of the large scale ETL kind of workloads, use a tool like Spark, use a tool like Daft. But if you're like ready to go into the machine learning world and just need to do, say, loading data into your models, then Ray is a great fit for that. I think where Spark and Daft come into play, it's really that if you think about the data engineering workflow, we have the bronze, silver, and gold tier, right? I think Spark and Daft really fit into that bronze and silver tier where things are a little bit messy. You're like, oh, like what is all this like grungy data that I'm working with? And also, I think where Daft fits the bill here is if you're like hardcore Python, I'm using Python to process all this like grungy data. I need that kind of interactive experience locally. I don't want to have to do with a JVM, and I want to eventually at some point like run this at really large scale, right? I have like a terabyte of data coming in through like my streams, and that's where I think Daft really fits in alongside something like Spark.
Cool. This is a great question. I don't think I have much to add. There is a request to basically put that notebook that you have there, by the way, Chen, make it available. So hopefully we can later on afterwards we'll update the LinkedIn and the YouTube links to this event specifically to include a link to the notebook. Okay, so just a quick call out.
Cool.
Sorry, just lost my question. Sorry, let's see. Okay, there's a benchmarking question. I don't think I want to ask that one because that's really diving into it. Okay. There is a question, and actually it was sort of answered, but basically is wondering, does Daft use data fusion under the hood? And I guess maybe we have been talking about data fusion a little bit from the Delta side and also from the Daft side. So why don't we clarify that a little bit? Yeah.
So we don't use data fusion under the hood. I know that there's a lot of interest in using data fusion today as kind of like a building block for a lot of applications. I think the way that we feel about it is that we want our application, again, to be that high level tagline, right? Simple, reliable, works on any data at any kind of scale. There are some design decisions within data fusion that make it a little bit difficult for us to use it for those use cases, including things like logical types on top of like physical types, including things like the execution model. Like we really wanted this streaming execution that Chan showed off to give us that really stable memory usage. And also the ability to just ensure that your stuff works without ooming. Yeah. Where ooms are like the banes of our lives as distributed, programmers, right? So yes, TLDR, short answer, no, we don't use data fusion under the hood, but there are components of data fusion that are interesting. For example, I know that the Iceberg Rust project now is looking to use data fusion.
Right.
And so if we adopt these projects, then yes, we will be, I guess, under the cover using data fusion.
Well, I mean, that's exactly what Delta RS is, right? Delta RS under the cover is actually already utilizing parts of data fusion. You don't, with Delta kernel RS, you don't actually necessarily have to use data fusion, by the way, but it is absolutely our default option, especially when you're doing some of the queries from the Rust crate directly. In other words, even if you're not using for Python, but there's a common approach where when we're just using the Rust crates directly because we actually want to write the code in Rust purely, then that's exactly what we're doing. We're actually going ahead and actually utilizing data fusion as our most common approach to actually query from Delta Lake. If you actually are interested in a data fusion query engine, actually the one I would actually remind folks there, Andy Grove is creating a project called Comet. It's a Apache Arrow Data Fusion Comet. I believe that's the full name of the project.
Long name.
Yeah, very long name. But long story short, it's actually quote unquote a Spark. They call it a Spark accelerator, but it's built completely in Rust and Data Fusion and Arrow. So, but that's actually an interesting project. And that also, the reason I call this one, it highlights the differences between what it's trying to do, which is very BI centric, versus what Daft is trying to do, which is very, very different modes, very different way of looking at the particular problems, which is exactly why Jay brought up the idea of okay, how does logical type works? What are some of the implementation details or assumptions that's making? In the case of data fusion, it was very much well designed for almost the BI style workloads. And again, why Comet is the data fusion is the basis for how Comet is being built. It doesn't mean isn't going to be any adaptations. It doesn't mean we're not going to leverage these systems. Like I said, you're already seeing Iceberg Rust, you're already seeing Delta Rust, already leveraging this pretty heavily as it is. So we're definitely going to be seeing a lot more compatibility and working closer with the data fusion community and with the Arrow community in general anyways. So yeah, just a quick call on that.
Yeah. Makes sense. One I guess visceral example to put in perspective why we developed our own engine is for example in Chan-Chan's demo, when we did that column of URLs into downloading data from those URLs, who knows what those URLs might hold, right? They might be 1 megabyte or like 1 kilobyte each, or maybe hundreds of megabytes each. Like you don't actually know. And so our engine is built in a way for us to be able to do these estimations up front, also like sampling to make sure that, okay, like things look good, and be very adaptive with all that, which is very difficult to do if we're tied into a opinionated set of like execution. But I think the beauty of data fusion is that it is so modular that you can kind of pick
Right.
exactly what you want from the ecosystem, which is something that we've looked into as well. But
Yeah. So I think that's it for questions for today. But just as actually, Chen, why don't we see if we can flip back to the slide so people can see the Daft Slack? Yeah, there you go. Perfect. There you go. So yeah, if you have any other questions, in addition, of course, to the Delta Slack, which I'm hoping y'all are on, why don't you also join the Daft Slack? I think that's it for today. Any last words from you two, since you guys are the guests?
no, yeah, try Daft out. Let us know. Let's try Daft plus Delta Lake, and also maybe am I allowed to call it Unity Catalog here?
Of
or-
course.
Okay.
Call it Unity Catalog.
Okay, try Daft, Unity Catalog, Delta Lake out. I think that's like it's such an interesting combination and allows you to do so many interesting things already just without a cluster, right? And you just run it on your laptop. It
Without
works
the JVM.
without the JVM, exactly. I think it's just like once you try it out, it's like so fast and iterative that it just feels like a new world almost of data tooling. But yeah, I guess that's the last thing I'll leave you guys with.
And just to call out Unity Catalog, we are actually doing a webinar with them on Thursday, April 24th, I believe. So tune into that on the Unity Catalog side to learn more about our integration with them. But yeah, thank you, Denny, for your time today. This is very fun to do.
Thanks very much. That's it for today. Appreciate it. And we'll see you at the next webinar.